this lecture, we'll focus on waves and sound. A wave is a disturbance that propagates from one place to another. The easiest type of wave to visualize is a transverse wave, where the displacement of the medium is perpendicular to the direction of motion of the wave. Vibrating strings on a guitar or piano wires are examples of transverse waves. In a longitudinal wave, the displacement is along the direction of the wave motion. Sound waves are longitudinal waves. Water waves are combinations of transverse and longitudinal waves. Wavelength, distance over which wave repeats, is measured in meters, or m. Period, the time for one wavelength to pass a given point, is measured in seconds, s. Frequency, the inverse of period, or the number of oscillations per second. It is measured in hertz, or seconds to the -1. Speed of a wave is a distance or wavelength divided by the time or period. This is also equivalent to wavelength times frequency. The symbol for wavelength is the Greek letter lambda. A 500 Hertz wave travels at 100 meters per second. What is its wavelength? This is easily solved using the speed equation. Speed equals wavelength times frequency. Solving for wavelength, we get speed divided by frequency. Plugging in, we get 100 meters per second divided by 500 hertz is equal to 0.20 meters. The speed of the wave is determined by the properties of the material through which it propagates. For a string, the wave speed is determined by the tension in the spring and the mass of the string. As the tension in the spring increases, the speed of the waves on the string increases as well. The total mass of the string depends on how long it is. What makes a difference in the speed is the mass per unit length. We expect that a lower mass per unit length results in a slower wave speed. The symbol for mass per unit length is the Greek letter mu. The speed of a wave on a string is equal to the square root of the tension applied to the string divided by mu. As we can see, the speed increases when the force increases and decreases when the mass increases. When a wave reaches the end of the string, it will be reflected. If the end is fixed, the reflected wave will be inverted. If the end of the string is free to move transversely, the wave will be reflected without inversion. Since the wave has the same pattern at x plus lambda as it does at x, the wave must be of the form shown in the equation on the slide. This equation describes where the particle on a rope is as the wave moves along the x-axis. The coefficient in front of the x is called the wave number. It is equal to 2 times pi divided by the wavelength and is measured in radians per second. The particle on the wave is also moving up and down like a simple harmonic oscillator, so it varies with time. The coefficient in front of t is the angular frequency we learned about when we studied simple harmonic motion. Sound waves are longitudinal waves, similar to waves on a slinky. Here, the wave is a series of compression and stretches. In a sound wave, the density and pressure of the air or the other medium carrying the sound are the quantities that oscillate. The speed of sound is different in different materials. In general, the denser the material, the faster sound travels through it. In general, the denser the medium, the faster sound. Sound cannot travel in a vacuum like empty space. There is no material for it to travel through. The speed of sound also depends on temperature. The speed of sound at room temperature, or 20 degrees Celsius, is 343 meters per second. We will use this as the speed of sound unless otherwise told. Sound waves can have any frequency. The human ear can hear sounds between 20 Hz and 20,000 Hz. Sounds with frequencies greater than 20 Hz are called ultrasonic. Sounds with frequencies less than 20 Hz are called infrasonic. Ultrasonic waves are familiar from both medical applications. Elephants and whales communicate in part by infrasonic waves.